This conference will now be recorded.
Hello everyone, today we will discuss consecutive reactions, and after that we will see what is collision theory and some related problems. In the last class we have seen what is parallel reaction. So in parallel reaction, two pathways that are going on simultaneously, it may be more than two also. And in case of consecutive, from the name it will be clear that as we are saying consecutive, so first there will be one step and then there will be another step. So the reaction in which reactant forms first an intermediate, and then this intermediate it forms the product. Now it may be one or many subsequent reactions. Here for simplicity we have taken only two steps. So first the starting material A is converted to the intermediate I, and after that it is converted to the final product. So here it is not that A is directly converted to P. That is not the case. First there is formation of some intermediate compound, then P is formed. So that is why these reactions are known as consecutive or sequential reactions, where product is not formed directly from the reactant. It is formed through some intermediate. Now if we take DADT, that is the rate of disappearance of the starting material A, that will be equal to minus K1, because when A is converted to I, then the rate constant is K1. So that is why K1 into concentration of A. Now in terms of intermediate, that is DIDT, the rate of formation of the intermediate, this will be equal to K1 into A. Now it is positive because in this pathway where I is formed from A, so as it is the one that is rate constant for formation of I, so that is why it is positive. But in the second step, that is rate constant K2, because of this rate constant now I is converted to P, that means now I is consumed, so that is why there is negative sign. So this part is for formation of I, and the second part that is for the consumption of, okay. And in terms of the final product dPdt, it will be simply dependent on the concentration of I, because P has no relation with starting material A, so that is why it is simply equal to K2 into I. Fine. Now detail integration we are not going, because that is not required. We will see what is the final expression. See, you can find some similarity with first order reaction, okay. So concentration of A at any time T, you can also put T here, that will be equal to initial concentration of A, that is A naught, multiplied by e to the power minus K1T. Similarly, from the second equation, we will find what is the concentration of I, and I is related to both K2 and K1. So that is why in this expression we have both mention of K1 and K2. Okay, but in case of A there is only K1. And when it is the concentration of P at any time T, then this is related to this equation in this way. Now P is basically, if you look at this, it is related to K2 and I. But in the final expression after integration, we can see here we have A0, K1, K2, all these terms. Now why it is so? Because I is related to K2, K1, A0. So that is why as P is related to I, so all these terms will be present. So these are the that is expression, final expression for the concentration of the starting material at any time T, then concentration of intermediate at any time T, concentration of the final product at any time T. Okay, these are the three expressions for starting material, intermediate, and product P. Now there will be a particular time which we are calling T max. So this time is that time where the concentration of the species, that is the intermediate, it will be maximum. So this time we are calling it T max, and the expression for T max will be this: 1 by K1 minus K2 ln K1 by K2. How we are getting this? Details we are not discussing. only the final expression is mentioned here, so that if we are getting in numerical, if these two values are given, you can directly find the value of Tmax when the concentration of intermediate is maximum directly from this equation. And the equation for the value of maximum concentration of the intermediate, that is equal to initial concentration of the starting material multiplied by K2 by K1 with the power K2 by K1 minus K2. So these two are equations for Tmax and Imax, that is maximum concentration of intermediate, that is possible, because here intermediate ultimately it is not present, that is when the reaction will be complete it will be converted to P, but there will be one moment when its concentration will be maximum, and that moment is basically Tmax, and the corresponding concentration of I, that is Imax. Fine. Graphical representation, so in all cases, that is first order, second order, then parallel reaction, we have seen graphical representation. For consecutive reactions also we will see the graphical representation. So this equation you have already seen in the last slide, that is the expression for the final product P at any time t. Okay, now in this expression we have both the rate constant for the two steps, first step K1, second step K2. Now two conditions may arise. One condition is when the value of K2 is very high compared to K1, and another possibility is obviously the reverse one, that is K1 is very high compared to K2. First we will see when K2 is very high value compared to K1, then what happens. So in this case the intermediate, now the intermediate we can denote by I or B, suppose A to I or B, then final product P or C. Concentration of P when K2 is very high. In this case, that is when we are applying this condition, what is its significance actually? The significance is, as here the rate constant for the second step is high, that is K2 is high. So it means that as soon as I will be formed, it will be consumed. Okay, so that is the reason, that is the rate of conversion of I to P, that is very high. That means K2 is very high. So if that is the case, now we can ignore K1. So when you are ignoring K1 in this equation, see now it will be reduced to equation 1 plus, it will be now 1 minus K2 because K1 will not be present. So it is like this, and this total term that will also be vanished, and ultimately we are getting this equation. Now here K2 will be cancelled, and ultimately we are getting A naught into 1 minus e to the power minus K1t. Okay, so see in the final expression for the concentration of the product P, we have only rate constant K1, not K2. Okay, now the corresponding plot. Here we have taken concentration in the y-axis, time in the x-axis, and concentration of A, B, and C. Here B is basically the intermediate, C is the final product. Okay. Now obviously with time the concentration of the initial starting material, it will decrease, that you can see, and here the amount of C, that will increase as we are increasing time, and this is the condition we have applied. K2 is very high compared to K1. So for example, if K1 is 1, K2 is 10, that means it is 10 times highly different. Okay. So if that is the case, now look at the line of B. As here it is mentioned that B is consumed as soon as it is produced. That means the change of B with time, it is not very drastic, because whenever it is produced, it is consumed. It is again produced, it is consumed. So there will never be a time when the concentration of B is very high. That is, the concentration of intermediate is very high. So that is the reason the nature of this plot is like this. Okay, so in you might get problem like suppose this condition is mentioned and there will be different plots given, and you have to recognize when the second step is very fast, then which plot will be the correct plot, which will match with this condition. So here we have the corresponding plot. The concentration of A is decreasing with time, C is increasing with time, but see the graph of B, it is there is no such time when the concentration of B is very high. Maximum concentration is this. See, this is very low. Okay. Any doubt? Another condition that is possible, that is the opposite condition, obviously. Now K1 is greater than K2. That is the first step is fast. In this case, all of the A, that is starting material, initially present, rapidly converted to the intermediate. And the second step, now it is slow. I is now slowly converted to the final product P. So again, we will take the same equation. Okay. In the previous case, what we have done, we have ignored K1, but now we will ignore K2. So the equation will reduce to, if we ignore K2, now it will be 1 by K1, and inside it will be 0 minus K1 e to the power minus K2 t. K1 will be cancelled, so ultimately the expression left is 1 minus e to the power minus K2 t. Now compare these two equations. In the previous one, it is 1 minus e to the power minus K1 t, but now it is K2 t. That is the only difference. Otherwise, it is same. And next we will see what will be the nature of the plot. Here K2 is higher value, and see, suppose K1 value is 1 and K2 is 0.1. That means K1 is 10 times greater than K2. Now again the same, that is concentration and time versus concentration versus time graph. Concentration of A, just like the previous curve, it is decreasing with time because it is starting material. And now see, just look at the difference. Here B is changing in this way, but now the concentration of B, that is the maximum point, it is very high. Compared to B, the concentration of C, that is final product, it is not so drastic. Okay, so here as A is quickly converted to B, that means there will be a moment in the reaction where the concentration of B will remain very high, because the consumption of B to A, that is very slow process. So that is the reason you can find some high concentration value of the intermediate during the reaction. Okay, so is there any doubt? Should I repeat? Next is steady state approximation in consecutive reaction. So why we are calling it steady state? Here intermediate is I. Okay, look at this reaction. A is converted to I, and the first step is involving equilibrium, but the second step there is no equilibrium, directly I is converted to P. So if we take the assumption, if a reactive intermediate I is present at very low concentration, okay, or the concentration is almost constant, that is with time there is no change in the value of its concentration throughout of the course of reaction or most of the course of reaction, then we can consider one assumption that concentration change of I with respect to T, it is 0. That means di dt, the rate of change of I with respect to time, it is 0. Remember, when it is this assumption we can take only when the reactive intermediate I is present at a very low concentration or it is having constant concentration. So any of these two conditions if fulfilled, then only we can say that I is now, it has reached steady state. Steady, that means there is no change in its concentration. That is why we are calling it steady state. I is now having steady state. Okay, so this is the approximation that we are making here. So when this approximation is present, see, as the first step is involving equilibrium, there is equilibrium sign here. So for the forward step, rate constant is K1, and for the reverse step, that is, as there is equilibrium, so I can also be converted to A, and for the reverse step it is K inverse 1, and for the second step it is K2. Now dA dt, this expression, it will be equal to minus K1A, because when it is rate constant K1, basically A is consumed, that means amount of A is decreased, so that is why there is a negative sign. But when it is the reverse process, that is when I is again converted to A, that means amount of A is again increased. So here we will have positive sign before K inverse 1 into I. Similarly, for dIdt, that is rate of change of I with respect to T, it will be equal to K1A, because rate constant K1, it is the formation for I, then minus of K inverse 1I. Why? Because when we are considering rate constant K inverse 1, it is basically for the consumption of I back to A. That is, it will form A again. And minus K2, because when you are considering K2 rate constant, basically it is for the conversion of I to P. That means I will decrease with time. So that is why there is a negative sign. And for the final product P, dP dt expression, it will be very simple. It is dependent only on K2. So that is why it is K2 into I. Fine. Now, as we have considered here steady state approximation, so we can say rate of consumption of I is much faster than the rate of production of I. Okay, that means the amount of I in the reaction medium, that will be always very low, because as soon as it is produced, it is consumed at a faster rate. So we can say that is whenever we are considering steady state approximation, the value of K2 and K inverse 1. So K2 and K inverse 1, these two are the rate constant for I, that is consumption of I, because when it is K2, I is converted to P, when it is K inverse, I is converted to A. So both these are for consumption of I, and as the rate of consumption of I is very high, so obviously the summation of these two rate constant, that will be very, very higher value compared to K1. Okay, so for steady state assumption, we can consider this condition. So when we are considering this condition, this equation, it will be equal to 0, right? And see here, instead of writing concentration of I, we have written SS as suffix. Why? Because it is SS means steady state. Now this equation, it will be converted to 0. Fine. So if it is converted to 0, you can write the value of ISS, that will be equal to K1 by K inverse 1 plus K2 into A, because these two terms, if you write in the right hand side, then you will take ISS common. So inside the bracket there will be K inverse 1 and K2, and it will be in the denominator. So after the approximation we have applied here, we are getting this final equation. That is, what is the steady state concentration of I? This is the value we can get from this equation. And if you consider this first equation, that is dA dt, and in place of I, if you write ISS. Now you know what is the value of ISS. From this expression you can write the value of ISS. So when you will put the value of ISS, basically this part, this is the value of ISS. Okay, we have taken from this equation. Now ultimately we are getting this equation, and how we are getting it. See, if you take, that is, just look at this expression. Suppose I am taking common minus K1A. So inside the bracket, what will have? 1 minus, then there will be K inverse 1 okay. Is there any doubt? Now this K inverse 1 and K2, if you bring it here, that is after calculation, it will be reduced to minus K1A, K inverse 1 plus K2 minus K inverse 1 divided by K inverse 1 plus K2. So these two will be cancelled. Ultimately, what expression left? K1, inside bracket we have K2, A, denominator is K inverse 1 plus K2. So see, this expression is same. I have written here, elaborated the part, but this equation ultimately it will be reduced to this equation. So this is the expression for dA dt minus K1 K2A divided by K inverse 1 plus K2. And here the other expression which is for A, that is concentration of A at any time t. Now if you are thinking where from we are getting this expression, basically we are getting this expression if we integrate this part, that is dA dt equal to this expression. If we integrate it, then finally we will get the concentration of A, okay, after integration. But integration details that is not required. So remember, this will be the final expression, and you can see it has some similarity with the first order rate expression, right? Any doubt? Is it clear what is steady state approximation? Now we have a related problem, that is a problem which is based on consecutive reactions. Here we have starting material A, it is converted to B. B is basically the intermediate, and first step rate constant K1, second step K2, second step B is converted to C. If the rate of formation of B is said to be 0, so it is another way of saying that we are considering steady state for B. So that is why we can say that the rate of formation of B, that is dB dt, that is considered as 0. That is the meaning of this line. Now, so when this condition is applied, then the concentration of B will be given by which of these expression? Okay. So here concentration of, that is dB dt, as we have written, equal to 0, but this can also be written as equal to K1 into A, because rate constant K1, that is the rate constant for the formation of B, so that is why it is positive K1A, and because of the rate constant K2, B is consumed to C, so that is why negative K2 into B. Now as this is 0, so it will be equal to, that is K1A, that will be equal to K2B. So finally concentration of B, K1 by K2A, and it is matching with which option? Tell me, look at the options. Which option is correct? This is the final expression. So concentration of B we have expressed in terms of K1, K2A. So all these options are basically involving K1, K2A, but there is difference. So which option is correct? Which one is correct? It is option 4. Okay, K1 into A by K2. Next, we are starting another topic, which is collision theory for chemical reactions. Chemical reaction, when it takes place, obviously there is collision among the reactant molecules. Look at this equation. We have taken starting material nitrogen gas, oxygen gas. There is some collision, and after that we are getting 2 moles of nitric oxide. Okay, so there must be collision between nitrogen molecule and oxygen molecule. Now this collision theory, it is basically based on kinetic theory. Now why we are discussing it? Because it can provide us qualitative explanation. See, it is qualitative, it is not quantitative. Qualitative explanation for chemical reactions and the rate at which they occur. So how collision is related to rate of the reaction? That is, rate is high, then what type of collision is responsible? Rate is low, what type of collision is responsible? All these explanation we can get from collision theory. The molecules of reactant, we will assume here as if they are hard sphere, because if we are not considering this assumption, then collision theory we cannot discuss. Okay, so we know that molecules are actually not hard sphere, it's not like a ball. Okay, but for the sake of this collision theory, we have to make this assumption, then only we can apply this theory. So this is the assumption, we have to consider them as hard sphere. See, suppose here we have 2 atoms of nitrogen, we have to consider as if it is a hard sphere. And the reactions are assumed to occur only when these spheres, that means the molecules, they are colliding with each other. Then only reaction is possible, because if there is no collision, reaction is not possible. Because in the product, there is bond between nitrogen and oxygen. So if nitrogen molecule is not interacting with oxygen, how bond formation between N and oxygen is possible, right? So that is why collision is required. Now the number of collisions per second per unit volume in the reaction mixture, that we will call collision frequency. So it is frequency, that means how many times it is occurring per second per unit volume. So this is the definition of collision frequency, which is denoted by capital Z. Now it is not that all the collisions are effective. It is not that any collision between N2 and O2 molecule, you will always get successful reaction. No, that is not the case. There is a term effective collisions. Not all the collisions are effective. Suppose N2 and O2 molecules, they are colliding with each other total 10 times. But out of these 10 times, only 2 times the collision is effective. Effective means which will result actual, that is bond formation between A and O, that is that what is the correct orientation for the molecule for in which when they will collide, then only successful reaction is possible. So first we will discuss what is energy barrier, what is activation energy, and then we will go to the second. But remember, both these barrier together decide what will be the criteria for effective collision. So effective collision, it is dependent on both these barrier. You have to overcome this barrier, then only product formation is possible. Otherwise not. The first point, energy barrier. Now here we will focus on activation energy and temperature. So suppose here we have 2 molecules, suppose 2 atoms, one is A, another one is B. They are coming to each other and there is some collision. but this collision is not successful, it is unsuccessful, because they are approaching to each other, they are colliding with each other, all these are fine, but they are not doing it with proper energy, with enough energy. So that is why it is not successful. But when they are colliding with each other with sufficient energy, then only the collision will be successful. In order to effectively initiate a reaction, the reactants must be moving fast enough so that they collide with sufficient force for the bonds to break. If there is no sufficient force, the bonds in the A molecule, suppose if you consider nitrogen and oxygen, so this bond must be broken. This bond must be broken. Otherwise, how nitrogen will interact with oxygen? But if they are not moving towards each other with proper energy, then even after collision, the actual bond formation between N and O is not possible. So the minimum energy with which molecules must be moving in order for a collision to occur in a chemical reaction, that minimum energy is called activation energy. Now look at this energy profile diagram. Y-axis we have taken energy, x-axis we have taken reaction progress. In the left hand side we have reactants. So suppose this is one is oxygen molecule, another one is nitrogen molecule. So both are same atoms. Now when it is they are covering this activation energy. This is the value of activation energy. That is the highest point, which is called activated complex. And if you see, this is the corresponding energy and this is the reactant energy. So this difference is basically the activation energy. So if the reactants, they are not possessing this extra energy, then they cannot make this activated complex, and if activated complex is not produced, product formation not possible. Now after this activated complex formation, when it is going towards right hand side, see, now we have product molecule. So all these are product molecules, fine. And here reactant energy is this point, product energy is this. So it means product is having lesser energy compared to reactant. So this is the energy difference between product and reactant, and this amount of energy will be released. That means the picture that you are seeing here enthalpy is negative, minus value. So energy is released. So this energy profile diagram, it is denoting an exothermic reaction. And if product energy is high compared to reactant, then it will be endothermic reaction. And in that case, energy will not be released. Energy will be absorbed. Okay. To this point, is there any doubt? Kinetic energy of a gas, we know that it is proportional to temperature. That is actually related to other chapter, that is gaseous molecules. Their kinetic theory is discussed. So kinetic energy is directly dependent on temperature. If you increase temperature, kinetic energy will also increase. So when we are increasing temperature, molecules will have enough energy and they will move fast and fast. Okay, higher is the temperature, faster will be the movement. So greater the temperature, higher is the probability that the molecules will be moving with necessary activation energy. Because when you are increasing temperature, basically you are supplying thermal energy. If you are not supplying thermal energy, the reactant molecules will be only at this point. But when you are applying excess energy in the form of temperature, then it will gain this amount of activation energy and they can make this activated complex. So temperature, that is a particular temperature we have to provide so that it can have this excess energy. This excess energy is activation energy. Now don't think that activation energy value, because for any reaction there is a specific value for activation energy. Okay, suppose A plus B equal to C, then X plus Y equal to Z. We have two reactions. For these two reactions there will be different values of activation energy. Now these activation energy values, it is not dependent on temperature, but it is true that when you are applying temperature, it will help the molecules to overcome this activation energy but that does not mean that activation energy that is dependent on temperature. That is the value of activation energy. Value of activation energy means the energy difference between this activated complex and reactant. This energy gap, this is always same. It is not dependent on temperature, but the molecules can have this energy if you are applying temperature. For a bimolecular, the greater the temperature, the higher will be the probability molecules will be moving with necessary activation energy for a reaction to occur. For a bimolecular reaction, that is, we have only two reactants, we are getting products. The rate of the reaction, it can be expressed in this way. And Z is basically, remember in the previous slide we have seen collision frequency, and the reactants are A and B, that is why suffix there is A and B. ZAB e to the power minus E by RT, where E is activation energy. Some more terms we have to know. Activation energy we know what is, but what is threshold energy? See, this energy gap, it is activation energy for the forward reaction, because this is reactant molecules energy, this is activated complex energy. So this gap will be activation energy for the forward state. EAF, F means forward. And if you are considering backward reaction, that is you are going from P to R, then this energy difference is the activation energy for the backward reaction. Now what is threshold energy? Threshold energy is when you add activation energy, that is this gap, with you add this energy gap with potential energy. That means reactant molecules, this is 0. So with respect to 0, reactant molecules already having this amount of energy, that is potential energy. So this potential energy, when it is added to activation energy, then we get this total value, which is known as threshold energy. So threshold energy is equal to initial potential energy of reactant molecules and plus activation energy. Similarly, if you consider product, then you have to add this amount of potential energy, because this is the potential energy for the product, and this amount of energy, that is the activation energy for the backward reaction. If you add these two, again you will get the same threshold energy value. A collision between high energy molecules overcomes the forces of repulsion and brings formation of unstable molecule cluster. So unstable molecule cluster is basically this activated complex. Because see, this is so high in energy, so it is not stable, it is unstable, it is formed for a fraction of second probably. Okay, so collision between high energy molecules, collision with proper energy, what it does, it overcomes the force of repulsion, because when two atoms are approaching towards each other, as there is presence of electrons, so there can be repulsion between electron density of each atom. So we have to overcome this repulsion also. So that is the reason proper collision with proper energy is required, so that this repulsion can be overcome and it can form this unstable molecular cluster, that is the activated complex, fine, which is having very high energy, that is why it is unstable. Now the lifespan of this activated complex, it is very small. Obviously it is small because it is unstable. So as it is unstable, it will break either into reactants again, that means it can move towards left hand side, or it can move towards right hand side, that means new substance products. So if it is going both side, that is both are happening simultaneously, then we will say that it is there is equilibrium, that is product to reactant, reactant to product. But if it is only moving towards right hand side, then it will be reverse. If the activation energy for a reaction, if the value is low, then the fraction of effective collision will be large. Okay, so activation energy low means we don't have to provide very high energy. The reactant molecules, they can collide with each other, and effective collision, that is the fraction of effective collision. Suppose there are total 10 collision. If activation energy is very low, Suppose there will be total 5 successful collision, but if activation energy is very high, maybe only one collision is successful. So when activation energy value is very small, then fraction of effective collision will be large and the reaction will be fast, and vice versa. That is, if activation energy is high, reaction will be slow. Activation energy depends upon the nature of the chemical bond. Okay, that is, if you are making that is A plus B, you are making product, so there will be some bonds in A that must be broken. So if the bonds are very strong, obviously activation energy is very high. That is why it is dependent on the nature of chemical. That is, the chemical bond, whether it is very strong or it is weak, depending on that activation of energy, it may be low or it may be high. And see, if it is free from effect of temperature. So this I have already said in the last slide, that activation energy value, this is dependent on the nature of the bonds that are to be ruptured. That is, the bonds that has to be cleaved in the reactant molecule, but it is not dependent on the temperature. Okay, but remember, temperature is helping us to overcome the activation energy, but it is not dependent on temperature. Another energy profile diagram. Now you will be able to understand the difference between exothermic and endothermic. So when it is exothermic, product energy is less, reactant energy high. This is the amount of energy which is released. So here energy is released, that means enthalpy will be negative. And in the second one, here product energy is high compared to the energy of reactant. So this amount of energy will be absorbed. Now enthalpy is positive. Okay. And in the previous case, activation energy is low, and here activation energy is high. Okay. Is there any doubt? This is the first point, that is energy barrier we have discussed. Next point will be orientation barrier. So in energy barrier, all the discussions clear? Next point, orientation barrier. Here molecular orientation and effective collision we will see. Suppose we have molecule NOCl. Okay. So here it is NO, this is Cl, NOCl, then NO. So this is the product. In product we are getting nitric oxide and chlorine molecule. Fine. So the equation, that is rate equal to ZAB e to the power minus E by RT. This you have already seen in the last slide. This equation predicts the value of rate constant fairly accurately for the reaction which is involving simple molecules. So if it is simple molecule, this equation will help us to find rate constant. But if it is complex molecule, that is very large molecule, then this equation is not enough. That is, this equation cannot explain. So there will be significant deviation from this theoretical value. That is, observed value and theoretical value, there will be deviation. The reason for this is that because molecules also need to collide with right orientation. So when it is complex molecule, proper orientation, that is to achieve proper orientation, that is difficult. If it is simple, it is fine. But if it is large and complex molecule, proper orientation cannot be achieved very easily. Now, what is effective collision? An effective collision is defined as the one in which molecules collide with sufficient energy. So sufficient energy, that is activation energy, that we have already seen. We know what how it is important. And the second point is proper orientation. So when we will call any collision effective, only when it is colliding with sufficient energy and proper orientation, then only the collision is effective. Now if you look at these three picture, here NOCl, this is NOCl, Now N and N, these two are approaching towards each other, but this is not effective collision because here N is, that is N is approaching towards N, but in the product we do not have any NN bond. So this orientation is not correct. Then in the second case, it is ClON. This is ClON. Now N and Cl, they are close to each other, but again there is no NCl bond in the product. So it is of no use that N is approaching towards chlorine. But in the last case, chlorine and chlorine approaching together towards each other. So oxygen. So now chlorine and chlorine approaching each other, that means the bond between chlorine and chlorine can be easily formed because chlorine is one of the product. So that means this collision will be effective, but not this one, not this one. Okay, so see, out of 3 collision, only one is effective, the other 2 are not effective. So that is the difference between just any collision and effective collision. Now ZAB is the collision frequency, and P another term if we introduce, which is known as orientation factor. Because why we are adding this new term? Because we have seen from this picture, it is clear that not just any orientation is perfect. There is, out of some 3 orientation here, as we can see, only one is fine. That means 1/3 of the total collision is important, not the other 2. Other 2 are ineffective. So this, how many collisions out of total collisions important, that idea we can get from this P. That is why it is called orientation factor, and we also have to add this equation, this new term in the equation. So, and sometimes it is also called steric factor. Okay, this is steric factor. So finally, this expression we are getting, collision frequency, orientation factor, both are present in this equation. Okay, is it clear? Here the question says the rate constant of a reaction is given by K equal to 2.1 10 to the power 10 to the power 10, then multiplied by exponential to the power minus 2700 by RT. It means that which of these statement will be correct? It is multiple correct type, so more than one statement may be correct. First we'll write this expression 2.1 10 to the power 10, then e to the power minus 2700 by RT. Now as the graph is log k versus 1 by t, so we have to take log both sides. Okay, now before taking log we will take ln because we have exponential term. So when you take ln, as in ln base is also e, so e will be cancelled. It will be ln k ln 2.1 10 to the power 10 plus ln e, then this whole term. So ultimately it will be minus 2700 RT. Okay, now ln, if you convert to log, it will be 2.303 log k, 2.303 log 2.1 10 to the power 10 2700 RT. Next what we'll do, we will divide both sides by 2.303. So as a result, what will happen? .303. So these two will be cancelled, and ultimately the equation that we are getting, log k log 2.1 10 to the power 10 minus 2700 2.303 R and I'm writing T separately. Why I am doing so? Because we will compare this equation with C plus mx. Here y is log k, c is intercept, which is this value, and x is 1 by t. This is x. So obviously m is equal to this value, that is slope. So here m, that is slope, is minus 2700, not r, t, it is 2.36. Now look at the options. Log k versus 1 by t graph when we will draw. Log k 1 by t. Now nature of the plot will be negative slope, and it is not going through origin, there is intercept. So the nature of the curve, it will be like this. This value is basically c, that is intercept. Intercept is log 2.1, 10 to the power 10. Okay, and slope is negative. This is the value of slope. First statement, log k versus 1 by t will be a straight line with slope minus 2700 by 2.303 r, which is absolutely correct. So this is true. Next, log k versus 1 by t will be straight line with intercept on log k axis, and the intercept is, there should be a bracket here. Okay, log 2.1 into 10 to the power 10. That means this is also correct because this is the value of intercept. So B is also correct. C, the number of effective collisions are 2.1 10 to the power 10. That means if you compare this equation with Arrhenius equation, k equal to a, e to the power minus a by rt. We know this is the number of, this is called pre-exponential factor, and this is actually the number of all the collisions. It is not the number of effective collision, but here it is mentioned number of effective collisions is this number, but it is not so. It is the all the collisions. It is not number of effective collisions. So this statement is not correct. False. Last statement, half-life of the reaction increases with increase in temperature. Half-life means what? Suppose A is converted to product P. Initially there is total 10 moles of A. So when 5 moles of A is converted to P, that means remaining amount is 5, and 5 is converted to P. So it means 50% is converted to P. So the time in which 50% consumption of the reactant amount is occurring, that time is called half-life. Now half-life when high, that means what? It will take more time, that is 50% consumption will take more time, half-life when high. And if half-life is low, that means 50% consumption will take less time. That means reaction rate is fast. So when rate is high, half-life will be low. That is inverse relationship. Okay, and we know rate is increasing with temperature. So when temperature is high, then rate is high, T half is low. That means T half is also related to temperature inversely. So half-life of the reaction increases with increase in temperature. That is not correct. Half-life will decrease with increase in temperature because these two have inverse relationship. So this statement is also false. Here correct statement is only A and B out of ABCD. Should I repeat it once more, or is it fine? Any doubt? Next topic is completely different, that is radioactive reactions. So we will not start it today, but I will mention one thing, that radioactive reactions, that is nuclear reactions, it is completely a different chapter. Okay, but why we are discussing it here? Because the kinetics that is followed in radioactive reactions, it is actually first order kinetics. So that is why there is questions related to radioactive reactions in chemical kinetics chapter, that is very frequent. Okay, so that is why we will have some idea about radioactive reactions, though we will not go into the details. We will focus only on the kinetics of these nuclear reactions, because it has some similarity with first order, though it is not fully similar. There is obviously some dissimilarity, because it is radioactive reactions. Radioactive reaction means normal chemical reaction. What happens, there is interaction between electrons of reactants, but when it is radioactive reactions, basically we have to consider the nucleus, not the electron, that is the outer environment of the atom. So that is the difference, but we will have some idea related to nuclear reactions based on the fact that it is also following first order kinetics. So we will discuss it in the next class. So regarding the whole class, is there any doubt? Should I repeat anything?
No, ma'am.
Okay, then we are ending the session here. Thank you for listening.
This conference will now be recorded.